So now you have your definition of torque. Now let's really answer the question, how much torque? Here we go. Let's calculate torque. Let's do it for the square loop, which we already used, or the rectangular loop, which we already used to calculate the forces. So we have B going this way. We have the current going around the loop this way. I think sides A and B, etc. We remember, though, that when we calculated the force, this one had a force out. This one had a force, this side had a force in. So we know now it's going to spin. It's going to turn around that axis of rotation. But let's calculate how much. Well, to get the torque, we can use the same four sides. We had 4 sides to calculate the force. Let's use 4 sides to calculate the torque. 1. R cross F. Well, if F is 0, the torque is 0. So torque 1 is 0 because there's no force there. 2. Side 2. R cross F. Okay. So R, let's think about what R is. R is the vector that goes from the axis of rotation to where the force is being applied. The force is being applied uniformly along this length. So it's really just this. It's that distance right there, from the axis to that side. And we know what that is. That's half this length. And for the bottom, this was B. So that's B over 2. So torque 2 is B over 2 is the R. The force was I little a times B. Now you're saying, wait, we mixed up little a and big and little b, but we were supposed to. For this one, for the force, what mattered was this length along this direction, A. For the torque, what matters is how far it is from the axis of rotation. So little a and little b are both in there. And remember, big B is the magnetic field. And then finally, which way? All right, well, R is going out, and R is going to the left, and F is coming out. So I didn't practice it ahead of time. Let's see. R cross F is up. It's up. So we also had a coordinate system, as I recall, X, Y, and Z, so it's in the Y direction. That's J hat, right? J hat. 3, torque 3, 0, because the force is 0. If you don't have a force, you can't have a torque. And 4, torque 4. And now you're wondering, is it going to come out to be 0? I hope not. Let's see. So torque 4, R cross F. R is now from the axis of rotation to this side. Like that. There's an R right there. Its length, again, is B over 2. Okay. And the magnetic field, or I'm sorry, the force was again IAB. And which way? R, and then R cross F into the board, up. Same direction, up. Also known as J hat in this case, in the positive Y direction. So the total torque on the loop, the total torque, it's a terrible tau, that's worse, is the sum of all these 0, 0. We have 2 in the J hat direction, and they're the same, just 1/2. The 1/2s go away. So we have A times B, that quantity, times I, the current, times the magnetic field. It's in the J hat direction. That is the total torque. Now let's see. It looks a little suspicious. This looks like the area here. That's a little weird. We'll address that in a minute. We figured out the torque on a square loop of wire. Let's do, just for fun, let's do an equilateral triangle loop with side A. Why not? So somehow, some equilateral triangle ended up sitting here like this. Side A, I won't write the A because there's a lot of stuff to draw. And it's sitting with a current going around it, current I, and it's in magnetic field pointing to the right, just like the square. Okay. I don't know if I need to draw that. Okay, so what is the force and what is the torque? So just like before, we'll give each side a number to help us keep up with what's going on. All right, so let's do them one at a time. What's the force on side 1? Well, let's see. So we got to think about what is L in this case. So the current's going around, so L is a vector pointing along this direction with magnitude A, right? Because the total length of that side is A. So the force is I L cross B, that's I. The magnitude of L is A, the magnitude of B is B. And then times the sine of the angle between them. Well, if this is 60 degrees of an equilateral triangle and that's 60, that would make that 60, which would make that 120. Okay? So if that's 60, this is 120, so we add the sine of 120. And then we need a direction. Let's see, so right-hand rule, if we have L going like this, then L crossed with B, this one has a force coming out. L cross B, the force is out. So I'll just draw the force vector F1 out of the board on that piece, right, F1. So I'll write out with a unit vector on it. We don't need to do X, Y, Z for this little problem. Okay, side 2. Side 2 has its L down here, like that. L is the same direction as B. The cross product, L cross B, is 0. So side 2 is 0. Side 3 is very similar to side 1. L goes up this way. Its magnitude is also A. So the force 3 is I, A, B, sine. It's the same angle between them, 120 degrees. And its direction, though, is in, right? Because if we have L cross B, the force 3 is in. So you can see, if we're pushing a force out evenly on this side and in evenly on that side, and there's no force down here, it's going to rotate, and it's going to rotate about an axis along the center. Since everything is nice and symmetric, we can just look at it and know the rotation axis. If this were all asymmetric, it'd be harder to figure out the rotation axis, but in this case, we know what it is. Okay, there's the forces. Now, let's think about the torque. So remember, torque was R cross F. Right? So let's see, what would torque be? Well, first let's finish this. This is square root of 3 over 2 I A B out. This is still 0, and this also square root of 3 over 2 is a sine of 120 I A B in. Okay, now we want to use that. So the torque is R cross F. Now remember, R is the vector from the rotation axis to the point that the force is applied. Okay, so that's actually changing here. This is the hard part of the problem. If you're talking about the force on this little piece, R is like that. If you're talking about the force on this piece, R is like that. On this piece up here, I'm going to start erasing things. There's R. So we're actually going to do a little shortcut in this problem because we have R changing. We're not going to do it in all of its detail. But I'm just going to tell you that if we were to add these up and do some sort of an integral, we'd find that this little piece, if we had the force per unit length, this little piece of force would apply no torque. This little piece of force would apply the maximum torque. That force times this full A over 2. Everything in between, it's just a linear increase from 0 to some maximum. So the average value, if you want to go with the average value, is the force times or cross with the radius crossed with the force at the center, at this point where we're at A over 2. See, here's a over 2 and a over 2. So at this point, a over 2, we want to use that value because that's the average value. So that is the radius vector we want to cross the entire force with because it's where it's the average. Okay, that's the little shortcut we're going to apply. Okay, so what is that radius vector? Well, this is a right triangle here. This is now 30 degrees. This is 90, and this is a over 2. So the sine of 30 is a half, so this is a over 4. Okay, so the r average vector we're going to use is a over 4 is the magnitude, and it's to the left. Okay, so we're going to cross that with the force, which is out of the board, and we know its magnitude. All right, so let's start multiplying the magnitudes of the two vectors. The magnitude of r, we just said, was a over 4. And then this one is the square root of 3 over 2iab times the sine of the angle between them. Well, that's 90 degrees, so the sine of 90 degrees is 1. These are actually normal vectors. This one is this way, this one is out. So if we have r cross f out, the torque is up. And that makes sense because it spins around the torque. So we don't have to add anything else. The torque is up. So it's a over 4 square root of 3 over 2 iab up. That's torque 1. Torque 2 is 0 because there's no force. Okay. Torque 3 ends up everything's the same. Same argument, everything works out the same. We're going to use the halfway point as the average radius. This radius here is r over 4. And it actually ends up in the same direction this time because radius has switched direction and the force has switched direction. So if we say r cross f, it's also up. So everything's the same. It's a over 4 square root of 3 over 2 iab. Okay? So what's the total torque? Add up the torques. So if we add them up, let's see if I can get this reasonably correct here in my head. If we add these two up, then those 4s are going to become a 2. So it's a over 2 square root of 3 over 2 iab up. We just added them. And now let's simplify it a little bit. And it becomes, let's see, I first, and then it's a square root of 3 over 4a squared. B up. So there is your torque. That looked like a lot of work to get something not so exciting. But let's realize a connection with the square. The square was I little a little b big B, right? And we said, hey, little a little b is the area. Interesting. Well, guess what the area of an equilateral triangle is? It's a square root of 3 over 4a squared. So when we did the triangle, we also got the same thing. It's the current times the area times the B field. What if we did a pentagon? Or I don't know, what is this? What am I making here? It's a hexagon. What if we did a hexagon? We could go through all kinds of horrible trig to do a hexagon. What would we get? We'd get the area here. Okay? It turns out that the torque, if you have a current loop and a magnetic field, is always basically equal to the current times the area times the B field. And you just have to get the direction right. So let's look at that a little bit more. The torque on any current loop then we can use the area to express it. So let's say, really any current loop. Let's just go ahead and do the simple one that you would first think about, which is a circle. Right? If this circle has some area A, and the current's going around like that, and the B field is like that, then the torque is the current times A crossed with B. That's how we get the direction of the torque, is the cross product is with the area vector. And it's that area vector we've thought about before, where it is, in this case, sticking out. You have to pick a direction you want to call positive of this area, and you say this way is out, therefore the area vector sticks out like that. So we know this is the case where the thing is going to spin, right? We have it sitting in the plane of the board like this. It's going to feel a force out this way, a force in that way. It's going to spin along this axis. The torque is going to be up, right? A vector across B points up, so we could draw the torque like this. And it really doesn't matter what the shape is. It could be a pentagon, a hexagon, a nonagon. It doesn't matter. Okay? If you want to find, if you have A and you want to find the direction it's going to spin, there's several right-hand rules that you can use. Okay? One is if something is feeling a torque and you want to know which way it's going to spin, put your thumb along the torque and your fingers spin. So one right-hand rule is thumb equals the torque and fingers equal the motion. If I see this situation, I know, oh, torque's that way, it's going to turn that way. We can also use this to figure out how magnetic a current loop is. So I told you early on that the magnetic field is loopy. Every time you have just a single wire, it makes a looped field around the wire. Whenever you have a current loop, it makes a field inside the loop. So how magnetic is a current loop? Let's ask that question. Sounds strange. How magnetic is a current loop? And the reason we're asking this question is a current loop is the fundamental source of magnetism. In a bar magnet, it's little atomic currents going around in a circle, things like that. So if we have a current loop, so now I'm going to draw it sort of in some perspective here, current going around like that, A vector like that. How magnetic it is means how does it respond to a magnetic field? It's all right here in IA. So we give IA its own special name. It's called the magnetic dipole moment. So mu is I times the vector A. And there is a convention to pick the direction of A. You don't just pick which way is positive. It's again the right-hand rule. If you have your fingers go around I, then your thumb is along A. So you had another right-hand rule. Fingers are I, thumb is A. A little hard to read. But the magnetic moment, or the magnetic dipole moment, or just the magnetic moment, is sort of the fundamental thing we use to characterize something's magnetic properties. We can rewrite our torque equation, actually, now in terms of this magnetic moment as simply mu cross B, because remember, mu, the magnetic moment, is really just I times the A vector. That's what we use to characterize how magnetic something is. So let's now think about a few moments here. So if we have just a B field going to the right, and we have a current loop that I'll draw sort of in the plane of the board, it's moment. We'll often abbreviate it just moment rather than magnetic moment or magnetic dipole moment. It's often just called a moment. Current goes around, so I know if the current goes around that way, the moment is this way by the right-hand rule. Here I have the moment, the same direction as the B field. The cross product is 0. This is the case where you'll have no torque. Okay? That's where it's aligned with the B field. So we know that this thing likes to be aligned with the B field. It doesn't feel any torque in that case. We could also think about, again, the case where it's in the plane of the board. Current's going around like that. I know that because I'm going to draw the moment as sticking out. Right? Current's going around, right-hand rule says the moment is sticking out. The B field is that way. We do have a torque. Which way? Mu cross B. So mu is out, B is to the right. We have a torque up. Which way is it going to spin? Right-hand rule. Torque is up, the fingers along the torque. I'm sorry, the thumb along the torque, and the fingers say it wants to spin that way. And let's think, if it spins that way, this mu vector is going to go like that. It means it wants to get back over here. So here the torque was 0. It's happy to sit like this. If you turn it to where the mu sticks out like this, the torque tends to push it back. back to this situation, back to that condition. So here, the torque is actually maximum. If you consider up positive, that's the maximum torque you're going to get when these are at 90 degrees, the mu and the b. We could turn it even further. We could turn it all the way anti-parallel to the B field. So now here, the I here, I'm drawing it like this is going back, and then mu could be in the opposite direction of the B field. Here, torque is 0 because mu cross B is 0. Their angle's 180 degrees. But it's different than this case. This is stable. This is a point of a stable, unstable equilibrium right here. Because although the torque is 0, if you get even the slightest little deviation from this position, which way is it going to push it? It wants to push it back over here. Right? If you let this torque come over to here, it pushes it back that way. So although the torque there is 0, that's not the stable position. This is the stable position. So what we really have here is the potential. We have a potential energy. We have a case where you can be here with no kinetic energy. You can turn it and push against the torque to align it this way. You've actually given it potential energy. And you can release it, and it'll turn back to here, and it'll have some kinetic energy. So you can go back and forth, just like a charge in an electrostatic field. Now, we said the magnetic field doesn't do work, but that was on free charged particles. This is a charge confined to stay in a current loop. That's why we can start to have start to do some work against the field. So let's write then that the potential energy of a moment in a uniform B, moment mu in uniform B, U is negative mu dot B. The potential energy is negative mu dotted with B. So let's see if that makes sense. When mu and B are in the same direction, that's your maximum dot product, and that's your minimum energy. When mu and B are opposite directions, that's going to be negative, and negative will make it positive. That's your maximum energy. And then here is in between. So you can start to think in terms of potential energy again if you have something with a moment, not a free charge running around, but a current loop, the fundamental unit of magnetism, basically. One interesting thing about this system is if you apply a torque to something, it doesn't just move and then stop. Right? It has momentum. When we had the square loop in the magnetic field and I switched on the field, it turned and it didn't really stop. It turned until it ran into something. So things don't really just turn when there's a torque to a certain direction. They're given angular momentum. They want to keep going. They don't want to stop. That's actually why compasses have oil in them. So a compass has this little needle that's trying to align with the magnetic field, similar to what we're talking about here. You'll learn about it in the next learning sequence. And if you were just to have that, it would turn to go north, and then it would just swing back and forth with all of its energy. It would basically go from here to here, back and forth, like a mass on a spring, going from kinetic to potential energy. But it has the oil in there to damp it. So if you look in a compass pretty close, you'll always see a bubble, and you'll see some liquid in there. And you wonder, why is that liquid in there? It's actually there to damp the motion. Otherwise, this thing would just oscillate back and forth all the time. So that is the end of this learning sequence. We were really just wanting to get down to really how does a magnetic field affect the motion of a charge, free charges and charge in a wire. And we got down to this thing, this magnetic moment. The next learning sequence, we'll talk about sources of the magnetic field. Where did this uniform magnetic field come from? How did you make it?